if you're new to us, please make sure you say hello before the end of the meeting or at the end of the meeting, and a big welcome to all our regular faces here. Now, the usual little preamble to say that for those of you at the university, your toilets are just outside the door there, and can we ask that you make sure your telephones are set to silent so they don't disturb the meeting. And for those of you on Zoom, it's lovely to see you as well, and I'm sure that you also are aware to keep your hands away from the space bar. Now, we've got a slight change of programme to our normal one tonight because we haven't got the presentation about the night sky because both of their usual presenters are not able to come tonight. But we do have an extra special treat for you because we've got Simeon Nelson from the University of Hertfordshire who's going to talk to us about an exciting project that they're getting involved with, and he's invited us to participate in it as well, so I'm sure that's going to be good. For all of you, those of you in the university and for those of you on Zoom, you can ask questions at the ends of the talks. Those on Zoom, you can submit your questions via the chat facility, and for those of you in the university, we will come round with a microphone so that everybody will be able to hear the question.
I'm not quite sure where to begin, but I'll begin with a little bit about myself, even a bit about my collaborators within the university, and hopefully enthuse enough of you to want to contribute in some way. So, but before I begin, I'll say that this is a research project, but it's also what they call an impact project. So in order for us to get funding, this sounds a little bit instrumental, but I promise you it's not. We're applying for funding, and we've got a bloody good chance of getting it, I think, from both the Engineering Sciences Research Council and the Arts and Humanities Research Council from Research Councils UK. But to get the funding, we want to make this an impact-led research project, which means we want to have an impact on what they call beneficiaries, recipients, audiences, stakeholders from the very beginning, from flagfall. So this presentation to you is a plea for your participation. All of you, any of you, the more the merrier, the more diverse, the better. And I'd also like to say that there's no such thing as a naive question. In fact, the naive questions are often the best because they're the questions asked by, they're the questions that actually really require some serious answering if they're not posed by an expert. So no question, all questions are very welcome. Over there you'll see a bunch of very primitive models. And no, it is not a prototype table from the John Lewis lamp shop. It is actually my sort of garage studio attempts to start to prototype what we're trying to do in a rather primitive way before bringing in the expertise of, so it's by myself, Simeon Nelson, Bill Martin, who is a spectrography expert, someone who can replicate the light of any star via his extraordinary fibre optic lab. I don't know if Bill or Hugh or Nuala are present. No. Hugh Jones. Now, Hugh is Professor of Astronomy, and Hugh has been a member of many of the teams that have made some of the most significant exoplanet discoveries, including Proxima b, the Proxima system, the Kepler system, and the TRAPPIST system. So he's someone who's been part of this kind of rewriting of the cosmic map that is currently going on that I find incredibly exciting. And last but not least is Nuala O'Flynn, who you might know, who's the outreach coordinator, who is a real gem. She's been absolutely brilliant in making this a project which hopefully will have enough outreach, enough inclusivity to engage, to spread it beyond academia. So the question of other worlds has occupied the artistic and scientific imagination since the rise of science. and observational instrumentation, not to mention the plethora of otherworldly entities and places of theistic and the place of theistic and animist cosmologies back into prehistory. So we all know that the night sky has been an enchanting, magical, extraordinary, otherworldly kind of dimension to earthly affairs ever since, possibly even for non-human species. And as Giordano Bruno, who unfortunately was burned to death at the stake for saying this, said in his book in 1584, there are countless suns and an infinite number of worlds orbiting around them, like the 7 worlds orbiting our own sun. I'm glad you don't get burnt to death for saying things like that anymore. So this speculation about other worlds reached fever pitch throughout the 19th century, with successive interpretations of Mars' surface as its details emerged from the increasing sensitivity of the telescopes brought to bear. Its apotheosis was in the work of Percival Lovell. So that's not quite supposed to be there. But anyway, look. So Bill Martin, expert in does anyone know how to say spectroscopy? This is not like ghost hunting. This is, he will capture the very faint signatures of our chosen alien worlds. The light is so feeble it will need to be amplified many thousands of times to light a small room. Underpinning research. So I'm going to show you a few things I've done as an artist, working with scientists. I've spent a lot of time working with scientists. And I tell you what, sometimes they're fantastic, sometimes they're not so fantastic. But I'm going to show you the fantastic ones. Sometimes, art and science are seen as somehow being at loggerheads in some ways, which I totally refute. Art is not just a cult of subjectivity, and science is not just a cult of objectivity. There is a lot of overlap in those two worlds. So my work on large-scale sonic and illuminated sculpture and video, connecting audiences with different cosmic perspectives and contexts from the very small to the very large. Bill Martin's work in optical fiber transmission, high-resolution exoplanet spectrographs, optical scattering, and biological signature detection. I don't think he's actually got a true biological signature yet, but he's working on it. I think my talk will has some overlap with the talk that's going to come after too, about spreading humans through the galaxy or the known universe. And Hugh Jones' work on radial velocities of local stars has contributed to the discovery and characterization of a significant fraction of the nearby extrasolar planets, including the discovery of planets including those orbiting the sun's nearest neighbor, Proxima Centauri, which is very exciting if you think that the absolutely closest star has something resembling a really good candidate for life. Then obviously this is a total game changer. So this is some previous work. This was shown at it was shown around Europe, around Australia, where I'm from, as you can tell from my incredibly thick Australian accent. And it was shown both outdoors against astronomical buildings, government buildings, religious buildings, and also inside museums. And what it is it's a kind of, I think of it as a cosmogony, an account of how the universe built itself, how it unpacked itself. And I'm not going to show you the video, there's no time, but it is it is starting off in a state of perfect order and gradually sliding ineluctably through greater and greater stages of complexity into something resembling pure chaos. And that's somebody contemplating it in a museum in Australia at a chaotic phase. But in between the pure order of the ordered grid and the total entropic chaos of everything just bouncing around in a sort of random Brownian motion, some very lovely patterns start to emerge. And if anyone has ever seen a murmuration of starlings, something of the nature of that, the local communication between particles can generate fascinatingly coherent and ordered global patterns, which I think I would not be out of order saying that is something that happens at both very large scales cosmologically and very small scales cosmologically as well. So this piece here, Cosmoscope, was a 3.3 meter orrery, or attempt to encapsulate the history of our knowledge of the universe with a sort of sanguine realization that the latest discoveries that we've made have just simply added to the darkness, or added to our levels of ignorance. Because if you think that James Webb is completely transforming our sense of a sense of order, or a sense of sequence, or a sense of where we're at in some sort of cosmic schema, it's really upended the apple cart, and now we're having to go back, and the textbooks of 20 years are likely to be significantly different from the ones currently in circulation, which does give one a sense of humility, that this notion that we're just filling in, crossing the T's and dotting the I's to fill in a sort of complete picture, seems to be receding further and further away from us, rather than us getting anywhere closer. And as an artist, I like to think that that's quite a good thing, because art is in the business of uncovering questions that seem to have been hidden by the answers. So in this project, I'm trying to uncover some basic questions, or we are all trying to uncover some basic questions. I'm not going to stick on, I'm not going to go on about past glories, but it was a very complicated thing to make. It was based on platonic solids, but it had a structural hierarchy. It had smaller versions of itself nested inside that. The idea of which was trying to, in physical form, trying to embody the notion of a local perturbation in space-time fabric giving birth to some other sort of universe. The notion of the universe as a kind of generative, organic entity, if one could be so arrogant as to think one knows what one means by the word universe, when in fact I've got absolutely no idea. So there it is. It had thousands of individually addressable LEDs that replicated. We worked with a physicist, Andrew Goodwin, who was an inorganic chemist at Oxford, who studies the very, very small, the molecular down to the subatomic in terms of material science. We worked also with Professor Simon Walker-Samuel, a imaging physicist at the Centre for Advanced Biomedical Imaging at UCL, who studies the generation and the flow of blood through cancerous tissue in the body. And I've missed out Professor, now I can't even remember his name, I'm very sorry, the cosmologist from Durham who runs the Eagle project, that giant supercomputer, which some of you may be aware of, that runs simulations of the galactic clustering, those sort of feathery tendrils that of how the universe sort of forms and deforms and reforms itself in a sort of ongoing process, which so I was trying to bring the micro, the meso, our level, and the macro into the same object with partial success. So context. So paragraph 2, flipping through an issue of Scientific American back in 1994 in Sydney, I happened across an orbit diagram of the first exoplanet system to be confirmed, 2 planets orbiting the pulsar. You wouldn't want to live on either of those planets, as I'm sure some of you are aware. But that stark diagram of a solar system other than the one I call home was an exceptionally unsettling moment of rupture and reformulation of the world I knew. I mean, it really had an emotional effect on me. I mean, not sentimental, but to realize that it's confirmed that we are not the only solar system out there, that it's like finally kicking away this sort of anthropocentrism of our historical sense of specialness. I think it was really, really quite a significant moment. Unfortunately, some of the artist friends I rushed over to show it didn't really kind of quite get it, but there you go. Thousands have been discovered. I must admit this. I must apologize because I was tinkering with this right up to the last minute because I've had to make lots of changes. Some of the slides are a little out of order. Thousands of exoplanets have been discovered since that momentous week in the mid-90s. Many, as you all know, many inhabitable orbits around their stars, not too cold, not so hot. And the thing about the Kepler telescope is its window on the universe is like a tiny, tiny sliver. It's a tiny fraction of 1 degree. So extrapolate that to a full 360, and we realize, as you all know, that there are billions and billions and billions of these potentially or likely habitable planets, which gives rise to the Fermi paradox. Why on earth have they not got in touch yet? Probably because we're too boring, or we're not communicative enough, or there's many other theories out there. The amounts of time are so vast that simply before any of these civilizations sort of runs its full course, and then there's like a lot of time where there's no possibility of communication. So on another project I'm doing, we coined the term the necrocosmos, because there should be the ever advancing spheres of telecommunications traffic from all these dead civilizations still propagating through the universe at incredibly faint bandwidths and frequencies and magnitudes. But if we had the right instrumentation to discover them, we could discover a veritable graveyard of lost civilizations. Perhaps it's a speculative question, one that I like to, sort of question I like as an artist. So these other planetary systems represent a huge perspectival shift, decentering our sense of place from out into the cosmos, and challenge us to rethink our human situation. From the perspective of a hypothetical observer on one of these other worlds looking out into their night sky, I really like this. If anyone's read War of the Worlds or any science fiction of that ilk. So any sort of observer stumbling across the faint signature of our planet, it would be a remote and uncharted exoplanet, and we would be the aliens. And I think that's one of the motivations of this project, to think that actually we are the aliens from the perspective of that other, if they're there, which we don't even know. That also is a good way of. This is a map of the supposed canals of Mars, done by Percival Lovell in his famous book, incredibly influential book. And this is quite unbelievably a 1962 NASA map, still with the canals, because of course until the Mariner probe flew past, we didn't know any better. That original kind of, what's the word, pareidolia, when you read a pattern into random data, still remained as a tantalizing possibility. Of course, we know now that Mars has no canals, and if there is any life, it's kind of going to take a lot more to discover. So sorry, back to the research questions. So actually, I'll do those later. I apologize for the slightly strange running order. So we are seeking your help in making a site-specific installation working with a direct fiber optic or line-of-sight link to a collaborating astronomical observatory, which for the moment would probably be Bayfordbury, or indeed the telescopes on top of the astrophysics right over here, dealing with the English weather. This installation amplifies the light of the chosen distant star in real time. Ideally, that is becoming less and less likely, actually, because to womp up a few photons to the trillions, quadrillions required to actually make a sort of proper light is probably beyond us. In fact, Bill says that to do that is one of you'd win a Nobel Prize. It's one of the holy grails of laser spectroscopy, to actually be able to amplify multiple bandwidths and emit them from a very faint source. Please also feel free to ask questions if what I'm saying sounds a bit outlandish, or please stop me, put your hand up, or just speak and ask for further clarification, because I'm trying to enlist your help. So I'd be very happy to take any questions during the talk. So It amplifies or replicates the light of a distant star in real time, so the viewer experiences that star from the vantage point of one of its orbiting exoplanets. Each of these suns obviously has a very different spectroscopic signature to our own, which brings me to my initial forays into different types of sunlight or starlight over here on the table. The viewer enters a light-fast black room and is dazzled by an intense otherworldly light apparently streaming through a window or an oculus, a direct bodily experience of bathing in the sunlight of alien worlds many light years away. And one example of this is the view of the sun from Earth has an angular diameter of about half a degree across the entire 360-degree sky. But if you were standing on Proxima b, apart from being fried by the electromagnetic flares that would fry you every few minutes, we're just conveniently ignoring that fact because we don't want to actually kill people in our installation. We want to give them a shockingly good aesthetic experience, not something that takes them to hospital or to the morgue. But Proxima will be 3 times as big, and it will be a very, very different color. It will be a kind of a warm red firelight type of glow. And without really knowing what the surface of Proxima b is like, there'll be lots of other speculation going on as well. But so if I go back to the research questions now, so what we're trying to do is give a really thoroughly multi-sensory embodied experience of this new knowledge of other worlds. So if you walk into a room, let's say it's Kepler 22b, that's also a red dwarf, I believe. Quite a different spectral signature to Proxima Centauri, but the light that left Kepler 22 started its journey to us about 486 years ago. So in a sense, what we're doing is when you open that door or close it behind you and step into the TARDIS-like apparatus or viewing booth, if you've suddenly been slammed, I'm not quite sure whether it's forward 486 years or back 486 years. I get really confused on that, being slightly dyslexic about these sorts of things. Maybe somebody, Hugh thinks it's forward, Bill thinks it's backwards, so even the scientists don't really know. But it's like sort of grabbing you by the scruff of the neck and flinging you across a lot of quadrillions of kilometers of space suddenly. So what effect might this have on that person's sense of their own personal and the wider human situation in a cosmic scheme? I have no idea, but that's the business of art, is to ask questions and is to ask questions that are in essence unanswerable, but that motivate us. It's those questions that motivate us that in a sense keep us alive, keep our brains functioning, and keep us attuned to the very strange universe we find ourselves in. What difference to our understanding of a scientific phenomenon? You see, when I showed this diagram from the mid-90s of that other solar system to other artists, they just went, so what? It's a drawing. And ever since I wanted to, that was a long time ago, 30 years ago, I wanted to take them by the scruff of the neck and throw them in one of these rooms and just to shut them up, just so that they can stop, so they can be actually humbled and amazed and transformed even by this experience, if that makes sense. So what difference to our understanding of a scientific phenomenon might an embodied experience make compared to the difference between reading about something? It's like reading about riding a bike and riding a bike, or reading about skiing or scuba diving and actually doing it, in a sense. It's the pulling of the rug of, it's not a mental, calm, rational process of, oh, I think I understand that, it makes sense logically. It's a kind of, what the hell was that? What was going on there? And it might take you a long time to kind of catch up with what happened. A bit like when you go to one of those rides at at the fun park. You know, they sort of throw you around and hopefully you don't vomit. We're not intending to make people vomit here. How close is it how close is it possible to get amplifying starlight in real time? How might differently sighted and abled individuals experience this? Because this is a multi-sensory installation where we're actually working with an expert in acoustics in the School of Creative Arts, Rob Godman, reader in music, who is incredibly good at, and I've worked with him many times before, he can make the back of a Morris Minor sound like Chartres Cathedral. He can give it exactly the same acoustic signature. So in order for this, presuming that there is some sort of atmospherics going on, for example, Proxima B, rather than it make you realize, because you sort of know where you are if you're blindfolded, you know where you are spatially. Sound is an incredibly powerful sculptural sense element. So rather than thinking you've been shoved into a wardrobe, you would have the sonic experience of standing on some sort of vast plain with or without the curvature of the planet in front of you, with a sun there in a dark sky or in some sort of hazy sky, depending on the atmospherics. And there'll also be smell. A lot of the comets smell like tar or even quite sort of earthy and sort of organic. So, of course, we can't know what you'd encounter, but we're going to try to, using the absolute latest research possible, give a sort of shockingly multi-sensory experience of what it would be like to open a door in this anywhere on Earth and suddenly be there. And it would also include haptics, the crunch of whatever's underfoot. You know, obviously we're not going to go for total veracity, because everyone who entered that box would probably die, which that's too much impact if you ask me. So differently sighted and abled individuals, people who might be colorblind, people who might be deaf, people who may have enlarged sensory apparatus on one level to compensate for a dearth on another. We're going to study how it impacts them as well. So I think I've done that one already. Apologies for the back and forth. I've put lots of my favorite quotes from cosmologists, and I love this one. A universe simple enough to be understood is too simple to produce a mind capable of understanding it, which is like one of those kind of devilish loops where you can't escape it. You can't, there's no coming back at that one. That's like an argument killer in a way, isn't it? What it means is that the questions about the cosmological questions are always going to be open, always going to be fresh, and we're always going to be confronting very dark sort of unknowns amidst the illumination of whatever it is we've discovered, which I also think is quite nice. For an artist, that's great, because that's what we want. We want lots of questions. We don't want artists. We want questions, and also for many scientists too. Certainly for Bill and Hugh, this is what gets them out of bed in the morning. This is what makes them feel actually they're doing something worthwhile. So I think I've already said that. Yes. So TRAPPIST-1, of course, these systems are incredibly different. Because they're often around red dwarfs, not always, but the majority appear to be around red dwarfs, you've got all sorts of added problems of electromagnetic flares, which would just kind of make your blood boil. You know, it wouldn't be pretty, put it that way. It would make Venus seem like a walk in the park. But there may well be ones that have the right kind of set of factors in place that allow enough kind of regularity or the right sort of rhythm to allow some sort of life to flourish. We really have no idea. I have a funny feeling we will never ever know if there's other life in the universe. That's my gut feeling. Be interesting to know what you guys think. Right. So this project is also motivated by when you realise that the same laws of physics are operating. You know, of diffusion, gravity, so that the lakes and seas of Titan, which is orbiting Saturn, which we discovered to our shock in 2005 when was it 2005? When what was the probe called? Does anyone remember? Huygens, thank you, the probe that actually, the lander that actually survived for about 40 minutes on the surface. Huygens, yeah. Huygens, yes, thank you. I mean, that was another big moment for me when these images came back. I thought, God, that could be the Bosphorus or the Black Sea, or that's just so familiar. That's like our own backyard. That's Earth. That's like what happens here. I mean, obviously, it's not a hydrological cycle. It's a cycle of liquids and gases at hundreds of degrees below zero, but the same sorts of erosions, the same pattern formation, the same river deltas, the same fractal edges, the same roughnesses, the same sort of laminar flows, turbulent flows, oxbows, all the things that flows of liquid do here seem to be occurring there, which both makes it very, very sort of uncanny, but also somehow curiously, it makes one feel a little bit more at home in the scheme of things. At least it does me. I don't know how other people feel. So, I mean, that's pretty well it. I mean, there's lots of, now we have lots of technical problems, because you cannot stick a sun in a box and get away with it. I mean, it's talk about Daedalus. That's like mix Daedalus with Pandora's box, and you've only got half the problem. So, without wanting to be sounding like a sort of arrogant know-it-all, the problem, of course, is that whether it's Proxima b or Kepler-22 or the Sun, whether it's single-digit millions or double-digit millions or more, the stellar light source that illuminates these planets is a very, very long way away. So that from our perspective of, like looking through a window, the fact that those rays are actually diverging, you can't notice because their divergence is so minute. But if you set up a light source a few meters away, you get massive divergence. So this is one of the, to make all the rays parallel coming through that window or whatever, we don't know how to do that yet. I mean, there's various diffraction gratings, there's various types of lenticular, prismatic sheet material, acrylic and others, that can sort of help, but nothing that's really going to do it. So if you have a spotlight, of course, all the rays are in parallel, but there needs to be light everywhere, right? Because you know what it's like when you're standing in an afternoon next to a window or the Venetian blinds. You see in a sort of interior, you see the rays coming through, and they're not diverging. They're sort of everywhere, but they're all in parallel. So this is something we have not solved yet. So we've been doing lots of initial experiments. I'm not going to go through the. It's very easy to calaminate light. That's what telescope lenses do. It's easy as pie. But how do you make something that's designed? If say we're talking about Proxima, so we put the LED light source in this internal space at X distance, and it has to be 1.5 degrees of the 360 view. How do you make all the light coming from that very small source parallel? I've got no idea. They've got no idea. Hopefully, without sort of resulting to too much sort of skullduggery, smoke and mirrors, we will have to bring atmospherics. It may have to be indirect light. We don't know, but we're going to get there. It might be like sunset. It might be the stellar or solar disk just peeking behind some sort of land formation or something that we create to kind of create the illusion that it's a sun without sort of having people laugh at us for producing this kind of installation with a glaring problem that it's obviously I could almost reach out and grab it. It's not millions of light years away. So it's a real tough one, but we will get there, especially with your help. You can widen the angle of the beam, but then it's no longer. So ideally, you get lots of rays coming through parallel. So actually, I've missed some of the drawings. I'm not quite sure whether that's there, but that doesn't really have much bearing. But it might. The double slit experiment. I don't know in terms of diffraction. So look, These are the models. So one idea is that is just a 45-degree, what do they call those things on submarines? Periscope, thank you. So to save space on the ground, and it's not trying to look like a church, by the way. Don't take umbrage at the pure coincidence of the shape. So you look through the window and you see a sun, because we need to get, the further away we get this light source, the greater chance we have of approximating something that's like parallel rays. And so I've just adapted a outdoor lighting system I had a few years ago. It hasn't been bad tested, don't tell anybody. I mean, obviously these are completely nothing, there's no sort of attempt to replicate spectral signatures, but you know, there are even stars orbiting very blue, planets orbiting very blue stars, but they're not going to have life because they haven't been around long enough, because those blue hot stars tend to be very, very young, short-lived, and extremely violent, and you wouldn't want to be anywhere near them. So red dwarfs probably are the main. The other issue, of course, if you look in there, you say, "Oh, isn't that lovely? It looks like your John Lewis light fitting or whatever." Where I'm actually corresponding with a Japanese company that makes a black, which is much blacker than Vanta black. Has everyone heard of Vanta black? It's the one made famous by the arrogant Anish Kapoor, who who made an arrangement with the company that makes it. He's the only artist in the world allowed to use it. And of course, other artists now come up and made blacker blacks. But there's an even blacker black than those blacks, which has 99.7% light absorption. And when you paint it on something, it just looks like it isn't there. It looks like there's a sort of hole in space-time. It's a very, very eerie effect. So in order to make a sun-like entity not reflect on the internal surfaces of the installation, those internal surfaces need to be as close as possible to absolute zero reflectivity. And they need probably also to, in a sort of topological sense, they need to be shaped in a certain way so that you don't have any surface that's closer to any other surface to have more reflection. The internal surface of this thing is going to be quite interesting, actually. I've been working on them today. I didn't get them in the presentation, but they look a little bit like Klein bottles, you know, like a vessel which sort of turns in on itself. It's not a full Klein bottle, obviously, but so that you keep the light source away from any kind of possible source. So you don't have surfaces that are closer and surfaces that are further away. So you don't go, aha, it's a light in a steeple, or a light in a cone, or a light in a hemisphere. You kind of are able to actually give this eerie sense of a stellar disk floating in space a bloody long way away. So, any ideas? Does it make sense? Any questions? Okay, I have to wrap it up. Do we have time for any questions?
Well, what I was going
I don't quite know how these things work. So
what I was going to suggest, because obviously Jerry is waiting to talk.
Of course.
What I'm going to suggest is, if you do have any questions, perhaps you could email them to me and I'll forward them to you. Would that be okay?
Be great.
And the same to the people on Zoom. Send your questions to me. I will forward them and get the answers and send them back to you.
And it's not just questions, it's actually
ideas. Yeah.
Like some of you might be having a brainstorm right now, keeping it to yourself, about how you could really do something quite remarkably simple and clever to get a bit further on toward this goal of having a kind of sun in the vastness of space, basically in a small internalized box. Mm-hmm. Thank you.
Well, it sounds an absolutely fascinating project that you're embarking upon there, and I'm delighted that you've invited us to contribute our ideas towards it. So
we need help.
You need help. Okay. Well, I'm sure that there will be ideas coming in. It's not like our group are not short of questions, but please send those ideas along. We'll keep the discussion going, and you can come back later on another time and tell us how things are progressing, and I'm sure we'll be delighted to take part.
What I didn't say, which I should have, is that Nuala, Bill, Hugh and I are going to schedule in some sort of co-creative workshops through the summer. I don't know when or where, but I'll be Nuala will be in touch with you. Yeah. And they're like sort of charrettes or kind of creative workshops and actually modelling what this thing could be. So if anyone's interested, the more the merrier is what we think, if anyone has time over the summer to do such things.
That sounds brilliant. So first of all, can I say thank you for giving up your time and coming along to speak to us tonight. It's lovely to get involved. So please, let's show our appreciation. Okay, I'll leave you to do a little bit of clearing up, and there'll be a little bit of activity going on down here. Okay, that takes us to the next part of our meeting. If anybody wants to get up, have a quick stretch, do so now. One or two of you. Thank you very much indeed for that. Well, our next speaker, I'm going to say needs no introduction, but that's not fair, is it? Because I'm sure many of you have known Jerry through our club. I mean, you've been a member of our club, how many years, Jerry? I was going to guess at 10. I remember you coming along to the cricket club over by the hospital, and from that point on, Jerry has been a tremendous asset to the club. I've been on presentations with Jerry, and I've always said that he has forgotten more than I actually know, and I think that's a pretty fair summation of the contribution that Jerry makes to the club. I'm sure that you've all recognised he organises the speakers for our meetings. That in itself is a tremendous job. And if I take this opportunity while we're just doing a little bit of clicking around to say that there is a change to next month's programme. Unfortunately, Ian Morrison is very badly ill and can't make it. However, Jerry has found another speaker for us. Christopher Crowe is coming along, and he's going to be talking about the Star Trek.
Yes. Okay.
Sorry, we just had a little aside there that Jerry joined in September 2014, so 10 years wasn't a bad guess, was it? As I was saying, the next meeting will actually be about the science in the Star Trek series. So I'm sure that's going to be another interesting one. So no more from me. I'm going to pass you straight over to Jerry, who's going to give us a very interesting talk, I'm sure. Over to you, Jerry.
Thanks very much, Alan. I believe so. Yes? Okay. Right. Good evening, everyone. So I'm Jerry Stone, a Fellow of the British Interplanetary Society and the Royal Astronomical Society. I am a freelance space presenter, and I run Spaceflight UK. And, well, I've been giving talks on space actually for over 50 years, having done my first one when I was 14 years old at school back in 1969, which is actually when this story begins. And my topic tonight has the rather interesting title of Island Zero, and it's about how we can set about producing space habitats. So I'm going to give a background to this and then talk about a new approach in the subject and a proposal which I helped put forward. And a major topic in this will be that of simulated gravity. And then I'll talk about the benefits of this. So, as I said, we start off back in 1969, just a couple of months after Neil Armstrong and Edwin Aldrin and Michael Collins landed the first men on the moon. And at Princeton University, there was a physics professor by the name of Gerard O'Neill. I actually met him in 1977 when he came to Britain to give a presentation at the British Interplanetary Society. And afterwards I was part of a small group that took him off for a meal and discussed his ideas further. But back in 1969 he gave an extra seminar in the new semester to a few of his new students. And he posed what was meant to be the first of a series of questions which would increase their interest in physics. However, he later said, as it turned out, once a first problem was chosen for discussion, it so occupied us that we never had time for a second. The question he asked was, is a planetary surface the best place for an expanding technological civilization? Well, the answer seemed obvious, but the students went off and did their research. And the answer they came back with was no, not on any planetary surface, which doesn't just mean not on Earth, but also not on the Moon, not on Mars. So the main reason is that on any planetary surface, you will lose the sun for 50% of the time. On Mars, a day lasts just half an hour longer than on Earth, although you still need to provide power during that time. But on the Moon, the night lasts for 2 weeks, and you need a major alternative source of power during that period. In addition, there's another problem with a permanent settlement that is not on the Earth. On the Moon, the gravity is only 1/6 of that of Earth, and on Mars it's just 1/3. And that, over a long period of time, will create major medical problems for the human body. So where should a structure be built if it's not going to be on a planetary surface? Well, to answer that, we need to go back 250 years. So if this is the Earth and that's the Moon and its orbit around it, the actual orbit of the Moon, in fact, any planetary or Moon's orbit, is an ellipse. But the calculation for that ellipse is pretty straightforward. However, if you add just one more object, the calculation becomes incredibly complex. And mathematicians tried for years to solve what became known as the three-body problem. So a series of answers was worked out in 1772 by Joseph Lagrange, and so they became known as Lagrange points. So L1 is between the Moon and the Earth, L2 is on the opposite side. Now normally, an object closer to the Moon will orbit the Earth faster than the Moon, so it'll pull ahead. And further away, it'll be going slower. But at these two particular points, objects there will move at the same relative position, the same relative speed as the Moon. If this was the Sun and the Earth, then L1 would be between the Earth and the Sun and is a perfect place to put a craft like the Soho Space Observatory to observe the Sun. On the other hand, L2, hidden by the Earth and looking out into deep space, is a perfect place to put another type of space telescope, such as the James Webb Space Telescope. There's also L3 on the opposite side of the orbit, but frankly not a lot of use to us. Now these three places are unstable. If you start to move away, you will continue to move further away. And so spacecraft in these locations need fuel for station keeping. There are two other points. L4, the same distance as the Moon, but 60 degrees in front of it, and L5, similar 60 degrees behind it. And these points are stable. If you start to move away, the combined gravity will pull you back again. You actually wouldn't be precisely at the point, but in an orbit around that point. And that is perfectly stable. So a number of designs were put forward for potential structures that might be built there, including one which I think looks rather like a 1950s lampshade. But the most useful shapes were, sorry, going the wrong way. Right, most useful shapes were a torus at the top, a ring, a sphere, and cylinder. So this is a design in a painting by Rick Guidis of one based on a sphere, which is in the centre of the diagram. What is not shown in this particular version are the solar panels that were needed to provide electrical power for this. But you can see there's a ring of mirrors. Some reflect forwards, some reflect backwards, to disc mirrors, which then reflect the sunlight through ring windows to the inside. At each end are manufacturing areas with radiators to get rid of waste heat, and the rings in front and behind are for agriculture. If we look through one of the ring windows, we can see to the inside. It is an inside-out world. We would take plants and trees and grow them. We would build houses, workplaces, schools, hospitals, entertainment centres, sports centres. There would be public transport. Everything required for a town of 10,000 people. And for comparison, that's just a bit smaller than Baldock. So we take and grow earth plants and trees. We would take bees to make honey and pollinate the plants. But we could leave wasps behind so we can have our barbecues in safety. Now, having said that though, there are actually reasons why we might want to take certain types of wasps, but not ones that sting. We'd certainly not take mosquitoes. And in fact, not only would we have a better environment than in many places on Earth, of course there would be no tsunamis, no earthquakes, no volcanoes, and we would control the atmosphere. Obviously, the ecology would be incredibly complicated. In fact, probably the most complex part of the whole project. So, as I've mentioned, and as you can see here, agriculture wouldn't take place in the main habitat area, but in separate agricultural rings. Now, in this painting, the rings are open to each other, but you could separate them so that you could have a completely different climate in different rings. Also, you could separate the sections of the rings and have the same crop at different stages of its growth rate. And because there's no overall summer and winter, it means a crop that takes 3 months to grow can be harvested 4 times a year, unlike on Earth. So we could have fresh strawberries all the year round. We wouldn't need cattle, probably. This is a picture from 50 years ago. We would probably have chickens, perhaps pigs, perhaps goats, and maybe cows for milk if we weren't getting all of our milk from goats. But beef, we now know we can actually generate from scratch. So following on from this design, NASA sponsored a symposium in 1975 which produced this ring design known as the Stanford Torus, because the conference was at Stanford University. And you may recognize this sort of design from the film Elysium. However, a major problem with that was, first of all, it didn't have a roof, so it was open to vacuum, but they needed that so that they could get spacecraft to fly in and land. But the main thing is, in Elysium, the structure was inhabited purely by the elite, and that is just simply impossible. Suppose you want to go out for a meal. Who's going to cook the meal? Who's going to take the plates away? If the streets are all maintained and cleaned by automatic vehicles, who's going to maintain the vehicles? So, no. So the large mirror you can see at the top reflects sunlight down to the outside of the central hub, where other mirrors then reflect the light inwards. So the inside of the ring is actually the roof. So this first design was at the same level as the spherical one. It would hold 10,000 people, and that level was designated Island 1. But a larger ring design was also produced that could hold 100,000 people, and that level was designated Island 2. So you can see that the ceiling would be sheets of angled glass so that the light would be reflected to the inside, so you wouldn't get main radiation coming directly through. So one difference here is that the agriculture, because there is only one unit really, agriculture would be in certain parts of the ring. But then there are the big ones, Island 3. These are the cylinders designed by O'Neill himself. Shown here as twin cylinders, they would be counter-rotating, so there's no overall torque. These would each be 4 miles in diameter, 20 miles long. And even this wasn't the theoretical maximum size, but something that O'Neill thought was about the limit of our technology. So agriculture here would be carried out in the rings. And again, because they're all separated from each other, you can have the same crop at different growth rates. Also, if you should get any kind of problem with a crop, it won't be transferred to the rest of it. So as a diagram of it, you can see the main cylinder, which is actually divided into 6 parts. 3 land areas called valleys, and 3 large windows called solars. So sunlight comes from the right-hand side of the picture. We have solar power stations there in the ring, and the sunlight is reflected off these large mirrors through the solars, the windows, to the inside. And to give you an idea of scale, in something this size, you would get natural clouds forming at 3,000 feet. One of the great advantages is, of course, that if you wanted to go mountain climbing, as you're getting closer to the center line, gravity decreases, so you have more chance of making the summit. Also, along the centre line, you could have human-powered flight. But you probably need some outer mesh so that you didn't suffer the fate of Icarus and fall to the ground. But certainly gliding in the lower areas would be a major sport. So here's a view along one of the cylinders. So although it would rotate, you would get continued sunlight because of the mirrors. And again, to give you an idea of scale, that's quite something. But now let's go back to the other end of the scale with the Island 1 design. How would we build such a thing? Well, what we would not do is launch all the material from Earth. It was estimated that it might need 500,000 tons, and launching that from Earth would be far too prohibitive. But we have a great advantage, which is that we know from the Apollo project the content of rocks and soil on the moon. And as you can see, a large part of it is oxygen, which we can extract for people to breathe, silicon for windows, iron, aluminium and magnesium for the structure, and other things, including titanium, at a higher rate than it is normally found in Earth soil. The moon has another advantage, which is no atmosphere, which means during the day you have access to the sun and you can power an electromagnetic launcher, which will not get slowed down by the atmosphere because there isn't any. And to get 500,000 tons would not actually need mining the moon, but simply using a bulldozer to scrape material off the surface. I've calculated that you only need an area 530 meters square by 5 meters deep. And to do this during 80% of the lunar day would take 18 lunar days, which is a suitable rate to be extracting the material in order to process it to do the building. It wouldn't be a continuous track, but you'd have units spaced at distances that would accelerate the magnetic bucket, as it's referred to. And that would be an open-ended container with the material that you're sending out. Once you've reached escape velocity, you then start slowing the bucket down again, and the material inside, non-magnetic, continues. You then recycle the buckets, put more material in and carry on. So one thing that you wouldn't send out in this way would be the silicon, because on Earth most glass is produced as float glass. So we have molten silicon on a layer of molten tin. And so that needs gravity. Otherwise it would all mix up. Well, there isn't much tin on the moon, but lead is there, and that has a similar melting point. So how big would a batch driver need to be? Well, O'Neill and his students made a demonstration machine, and the first one produced an acceleration of 33 G. But if you were to use that to throw material out from the moon, it would need to be nearly 9 kilometers long. Mass Driver 2 at 500 G would only need to be under 600 meters long. And they even produced Mass Driver 3 with an astonishing acceleration of 1,800 G. And that would only need to be 190 meters long. In fact, we'd probably make one longer than that, so that there would be more time during the acceleration to correct the trajectory. Now, O'Neill deliberately restricted the design of Island 1 in two ways. Firstly, by cost. It had to be capable of being built for no more than the cost of the Apollo project, or the equivalent. This was so nobody could say, well, it's a nice idea, but we can't afford zillions of trillions of dollars. The other restriction was that it had to be capable of being built with the technology available at the time. So nobody could say, well, it's a nice idea, but it depends on this and this and this that we haven't invented yet. The point is that given the initial funding and the will to go ahead, this could have been started in the 1970s. So the obvious question is, why wasn't it? Well, although most of the material was intended to come from the moon, we needed the initial infrastructure to begin the development, which would mean launching material and equipment from the Earth. And this was intended to be provided by the space shuttle, which, according to NASA's initial releases, was due to fly every 1 or 2 weeks and bring the cost of reaching orbit down to less than $1,000 per pound. In reality, the low flight rate and incredibly high cost of maintenance meant that that just simply wasn't possible. But a few years ago, I thought, it's now nearly 40 years since the original design, and our technology has advanced considerably since then. We have new alloys. We have new materials that didn't exist, like graphene and carbon nanotubes. We have new processes like 3D printing. And our computing and robotic technology is several orders of magnitude beyond what it was back in the 70s. So I thought, if we were to start this project now, we could do it more efficiently and probably cheaper relatively than we could back then. So I made a proposal to the British Interplanetary Society to set up a project. I called it the Space Project. Study Project Advancing Colony Engineering. That's just my sense of humour. I must say, I actually prefer the term settlement rather than colony for historical reasons. And I started the project by setting not goals for the team of volunteers that gathered together, or saying what topics should be covered, but asking them to come up with questions that would need to be answered for us to achieve this. And I put the first 2 questions to the team myself. All habitat designs, I mean, there were many of them by that time, but they all assume it will rotate to provide 1G. And my question was, do we need 1G? What about 0.9, 0.8, or even less? There would be less stress on the structure, and so less material needed to build it, and also less stress on the inhabitants, on their cardiovascular system, their skeletal structure, and their muscles. They would be healthier. Over a long period of time, they would live longer, they would grow taller, and we need to take that into account in the architecture, higher doorways and ceilings. But the associated question is, how much can you reduce the gravity before it becomes a problem rather than a benefit? And the answer to that, as they say on QI, is nobody knows, because we've never done it. And obviously we would need to in order to get the medical research. And we need that before we can finalize the design for the main structure. So, I also pointed out it's obvious we wouldn't begin by building an Island 1. We would need to extract the raw material, mostly from the surface of the moon, and we might get some from asteroids as well. We would then need to process this material in order to extract the different elements. We would then need to use that material to manufacture the components of the main structure, panels, girders, windows, and so on. And then we need to assemble the whole thing. But apart from all that, we would also need living quarters and workshops and offices for the team doing all this. So this would be a much smaller structure. And as we've had Island 1, Island 2 and Island 3, because this is going in the opposite direction, we called it Island 0. Ideally, it would be made of modular components. It would rotate to provide simulated gravity, and they would also do some growing of their own food there, and also construct some demonstration manufacturing facilities. So, being under simulated gravity, well, that wouldn't apply when they're outside the structure working in weightless conditions. But the rest of the time, and particularly when they're sleeping, the major part of the entire day-night cycle, they would be under gravity. So they would not have to conduct 2 hours of exercise every single day as they do on the International Space Station. I've actually referred to these small units as porter cabins in space. Gives you an idea of their use. So why have simulated gravity? Because the big problem without it is the detrimental effect on the human body. And without having the body needing to work against gravity, the following issues arise. Blood flow is no longer pulled to the lower part of the body. As a result, astronauts who arrive at the International Space Station, within the first couple of days, their faces puff up. And it also affects the flow of blood around the body. Muscles are no longer having something to push against, and consequently they weaken, particularly leg muscles. And the skeletal structure itself also weakens from not having to push the body upwards. This results in effective osteoporosis, which is a major study on the International Space Station. And the cardiovascular system also has less to work against, and so the heart weakens. In fact, the heart changes its shape from an oval, like a water-filled balloon, to a round ball, like an air-filled balloon. And this is why they need to do all of this exercise each day. It also means that we've had to spend about $100 million ferrying all of the exercise material up into space. So with Island 0, it won't be necessary to launch that equipment, or for everyone on board having to use it for 2 hours every day, so they can spend their time doing more useful activities. So I suggested that the basic units of Island 0 would be cylinders, 15 meters long with a diameter of 4.8 meters. They would be inflatable so that you could launch more at once from the Earth. So that would be cheaper. And Bigelow Aerospace has already not only developed inflatable structures, but 2 of them, Genesis 1 and 2, have already been launched and are still in orbit. They also came up with a larger one, the B330, because it would have an internal volume of 330 cubic meters. So the one that I'm proposing is smaller than that. And also Sierra Space have developed an inflatable structure. It hasn't been launched yet. Also Max Space, whose founder, Maxime de Jong, built Genesis 1 and 2 for Bigelow. And I chose the size because the units would fit into the payload bay of Skylon, which is under development in the UK. This initially would be an unmanned craft, but its key are the two engines at the end of the wings, the Sabre engines. These are composite jet and rocket engines. So they will start off as jet engines, launching on a runway and reaching about Mach 5, 25,000 feet. And at that point, instead of taking in air from the front, the nose cones would close off and it would use the onboard liquid oxygen and liquid hydrogen, and they would act as rocket engines. The advantage of this is that you do not have to carry all of your fuel with you from the ground, and as a result this could be the long dreamt of single stage to orbit vehicle. Once in orbit, it would open the payload doors, release any payload, then close them and come back and return to Earth. Although it would need a specially hardened runway to take off, when coming back, reaction engines who are working on this have actually said it could land on a grass runway, which is quite amazing. Later versions could have pilots, and the payload bay could take up passengers. So the Skylon payload bay will accommodate a 4.8 meter diameter unit, but it's only 11 meters long. But that doesn't matter. If a 15 meter unit can be compressed to just 2.85, then 4 can be stored in the payload bay. Unfortunately, Skylon can only launch 15 tons, which would only be one module probably. Although later versions of inflatable units could be much lighter, much less mass, I should say. But the payload bay of a Falcon Heavy rocket, which didn't exist when I began this study, has an internal diameter of 4.6 meters, so you could squash it a bit more, but it can carry 63 tons, so it really could take 4 of these units at once. So the original proposal was that we'd have 8 of these units fitted together as a ring of modules. And at 5 meters in diameter, which was the very early design, then this would give an overall diameter of slightly more than 45 meters, a radius of just over 22 meters. But then I did some calculations on the effect of diameter and different rotation rates. And it turned out that with a radius of 25 meters, then even at 3 RPM, you'd only get 1/3 of a gravity. You'd need 6 RPM to get 1 G. And 6 RPM, 1 revolution every 10 seconds, I thought that's not going to be really tolerable. So in order to have a reasonable rate of just 2 RPM, then in order to produce 1 G, we'd need to expand to a radius of 225 meters. But to have a ring even with a slightly smaller radius of 200 meters, would need 84 units. So it would no longer be a low-cost operation. And in any case, we just simply don't need that many. So how could we keep the number of modules down? Well, I then suggested that instead of having the units like this, that we would rotate them and arrange them radially on tethers, and by increasing the size of the tethers to 200 meters, this would provide the system that we need. We would have an outer safety ring, which would also be a means of getting from one unit to another. If this was a tube 2.4 meters in height, you could just walk along it. This is actually just to give an idea of the configuration. It's not to scale. So the individual units would be divided into various levels, allowing for crew accommodation and areas for experiments. At the top of the module, the unit would be tethered to the central hub, which would consist of other modules set at right angles. As parts of the central hub would be counter-rotating, then the units attached to this could provide safe docking ports. To get between the levels within a unit, people wouldn't use ladders. There'd be spiral staircases fitted to the interior of the outer wall. If you compare this volume, 270 cubic meters, so 8 units would give 2100 units. Compare that with Destiny, which is the largest module on the International Space Station. You can see it gives much more volume. And in fact, overall, the ISS has only just over 1,000 cubic meters of habitable volume, which is less than a half of what this would provide. So this is a scaled diagram. We would also, though, need access tubes between the central hub and the outer modules. Well, if they were straight, people and equipment could be falling at 0.9 G or more at the outer end, which might be acceptable perhaps with ropes and pulleys when transferring equipment, but they would hit the walls due to the Coriolis effect. But I thought it would be impractical and expensive to install lifts. So an alternative idea would be to have a series of tubes approximating a curve. So as you move further out and gravity increased, you would become more and more towards walking fully upright. And we'd have 3 other sets rather than 8 in total. Now I discovered that this had been proposed in a design by a man named Herman Nordnung in 1928. So it is most definitely a practical possibility. Now, unfortunately, this is not going to play, which is a shame. Okay, so I then thought, well, if instead of being radially outward, if the units were actually horizontal, you could divide each one into 2 levels, which would make more efficient use of the space inside. And if the connecting tube was actually connected to the lower level and the access tubes connected to the higher level, they could look like this. If you increase the rotation from 2 RPM to 3, then you'd only need a radius of 100 meters instead of 200. So that means the unit would be shrunk from this to this. We'd probably only need 2 sets of access tubes. The outer ring would be smaller, so overall it would be cheaper to produce. If we expand that view, then this shows the central hub through the middle, which would also have solar panels and heat radiators. But further studies have shown that a rotation rate of 2 RPM is not necessarily required to achieve 1G at a rate that crew members can tolerate. In fact, studies show there is considerable confidence that space settlements can rotate at up to 4 RPM. So this translates into a system size of around 55 meter radius to produce 1G. Or, they said, even 6 RPM. I am still not happy with that. No. But these rates have been verified, particularly by Al Globus, who's the world leader in this, in his book, The High Frontier, An Easier Way. And it showed that in the right location, which is equatorial low Earth orbit, in other words, unlike the International Space Station, whose orbit is inclined at 56 degrees, you're actually going directly over the equator. And the advantage of that is that space radiation is so much lower there that you would hardly need any shielding at all. So the sizes I just mentioned are far smaller than previous designs and take us back to the original structure. At 6 RPM we could have a unit like this, and it wouldn't need an outer ring, just connectors. But at 4 RPM we have a much smaller radius than the 200 meters that I originally described. In this version, at 3 RPM, I've added more solar panels. And the reason for that is in order to power additional modules. So we probably wouldn't have it at a 100 meter radius because we don't actually need 1G. We've got all the medical data we need of people working under 1G down here on Earth. But for 0.9G, we could bring the outer radius down to 90 meters. And we could also have units at 80 meters and 70 meters, which would provide 0.8 and 0.7G. So our unit would be slightly smaller, rotating at 3 RPM with a radius of 90 meters. The outer modules would provide 0.9G. Coming in slightly, we'd have 0.8G with another one on the opposite side to balance it. And closer still, at 70 meters, we'd have 0.7G. The great advantage is that we get these different levels of gravity simultaneously without needing to slow the unit down or speed it up. So this would enable us to gain the medical data needed. We could carry out the same experiments on different inhabitants at the same time and compare the results. In fact, Gerard O'Neill himself made it clear that that experimentation for figuring out the right and best gravities for humans, animals and plant physiology was crucial to long-term space living. Some of the other modules could be rented out to universities or companies for them to do their own work. We could also use some for space tourism, and all of that activity would bring in income. So all in all, the Island Zero concept offers a lot of opportunities. There's one other adjustment to the design. Let's look at the access tubes. I originally said that installing lifts would be expensive, but recently I came up with a new idea. A simple lift. Instead of an enclosed room on cables, it would just be a platform moved on a rack and pinion. So the structure would look like this. And this vertical option could deliver people and equipment from the central hub to the outer modules, and also to the upper or lower levels of each module. So it would just go like that. And why is there a top as well as a bottom? Because of course once you reach the center, you could then carry on in the opposite direction, well, in the same direction, but going down to the opposite units. The other change was the main construction. Inflatable units would require quite a thick wall, I was told, which would cut down how many could actually be launched at once. An alternative to that would be to allow a number of units to be launched together that would be made of expandable units. And these could be used for the main modules, which could be expanded to give a flat floor, but curved. In addition, the outer ring itself can be made of similar units, which would be narrower and longer. In both cases, that would improve the efficiency of the internal volume usage. And for the lift shaft, again, it would be possible to use cylinders. So the resultant structure would change to this. And in addition, some extra radiation shielding could be included at the very outermost module. There's another possibility for Island Zero, that a smaller version starting at 4 RPM could be used to take crews to Mars. And we could adjust the rate of rotation during the 7 to 9 month trip, so that by the time they approach Mars, they'll be at 1¼ RPM, providing the equivalent of Mars gravity, 1/3 of Earth gravity. So the crew will already be acclimatized to that when they land. So the landing craft would be attached to the central hub there. Otherwise, NASA estimates that they would need to spend 2 days simply acclimatizing to the gravity, and that is basically wasted time. And of course, they can re-acclimatize to Earth gravity on the return. One possibility for the building of something like Island 1 was that the inhabitants could then build large solar power satellite units. And these would take energy from the sun and transmit it by microwave down to the surface of the Earth. The beam would be spread out over large receiving rectennas, that would be perhaps 7 kilometers in diameter. That means the beam would be so weak that any animals on the ground or any birds flying through the beam would not feel it. it would be about half of the intensity of sunlight. And the microwaves could then be converted into electricity on the ground and fed into the grid, providing 10 million kilowatts at each site. Now, in January this year, NASA issued a major new report, 90 pages, on space-based solar power, showing how much they are in favour of it. This referred to two particular reference designs, not intended to be built from something like an Island 1, but again, because of advanced technology, to be manufactured in small units and launched from the ground and assembled in orbit. Well, if we're going to do this again, an Island 0 for the assembly crew would be very useful. And NASA has a huge interest in commercial activity in low Earth orbit, where again, Island 0 could do that. So Island 1, a major benefit of that would be moving construction off the Earth, because having built the thing, we would continue to get material from the moon and use that rather than mining the Earth, which would mean less pollution on the Earth. We would use power, materials from the moon. We'd have power from the sun rather than burning gas, coal and oil. And as a result of reducing pollution on the Earth and reducing our production of carbon dioxide, the Earth would get to be a better place to live. And as the resources available from the moon and asteroids far outweigh those from the Earth, and the living space gained from the construction of large habitats would outstrip the global Earth rate, it means we will never run out of room. And also, there will be no need for any nation to attempt to claim resources from others. In other words, the threat of warfare would be reduced. So if there's any reason for going into space, surely that has to be it. This was effectively summarized in a quote from Frank White, who wrote The Overview Effect, about the effect of seeing Earth from space on the astronauts. He said, "War and space exploration may be mutually exclusive, because if one occurs on a massive scale, the other probably will not." Now, we know which way we'd like that argument to go. And perhaps the development of Island 0 may well be the best way of moving forward in this activity. So for benefits of Island 0 itself, it will be constructed using current technology. We can do this now. We don't have to wait 20 years. We can launch it using current boosters, and once Starship is fully available, then that will bring the cost down even more. We can rotate it to provide simulated gravity, but we can operate at different gravity levels simultaneously. And I haven't seen any other design that has proposed that. So that will provide the essential medical research that we need for the future. And it can also house crews that are involved in commercial space activities. Now, obviously, more work is needed to finalize the design, but a major factor is that this is not like a proposal for, say, a new space telescope. This is a structure that has simply never been built before, and will result in people living and working in conditions never experienced in space. So I'm putting together a proposal that the European Space Agency carries out a feasibility study to verify the concept of Island Zero. Meanwhile, we have a title and a logo, as you can see on my new tie, which I had made up a couple of weeks ago. And bearing in mind that mankind's expansion into space could help solve many of its major problems here on Earth, including a reduction of wars, it seems appropriate to slightly amend the logo. And we have a slogan, courtesy of Blade Runner. And I hope the sound is going to come. No, I'm not getting the sound out of the... Never mind. So there's the slogan that we have. So if anyone wants more information about this, I have a summary file, and if you let me know afterwards, I'll be happy to send it to you. I have produced an abstract of this presentation, which I've sent to the International Astronautical Federation, which is having its annual convention, which takes place in a different country every year. And that will be in October this year in Milan. So I will know by the end of the month whether it's accepted, and if so, I'll be off to Milan in October. But thank you very much. I hope you found this interesting. And if you have any questions, I'll be happy to take them. Thank you.
Okay. First of all, is that on? Yeah. First of all, I'd like to say thank you very much indeed, Jerry, for a fantastic talk there. I'm conscious of the time, so let's just take one question from the floor, one question from Zoom. Anybody else has a question, please email them in and we'll pass them on. I have got a question on Zoom. We've got one here. Well, there was one earlier, and that's moved up the page. Let's just... Okay, I won't fiddle about with computers. We've had enough fun with those this evening. I'll say to the Zoom people, we will find all your questions, hopefully, and forward them to Jerry. If you haven't heard by the end of the week, send them in again, because that means they've gone somewhere else. Can we have a... Let's just take one question from the floor. Can I come behind? Okay, thank you. Anyone on the floor got a question? Oh, sure.
You say you're going to process the stuff you bring up from Mars in space. What do you do with the rubbish? I mean, aren't you going to get space junk writ large?
No, it's a very good question. Sorry, we're talking about material from the moon. But any waste material will be put around the outside of the structure to act as extra radiation shielding. So that's for the Island 1 unit, because that's going to be out at the distance of the moon and therefore will not have the Earth's electromagnetic field to protect it. So all of the waste material will be used for radiation shielding.
Okay, as I said, I'm sorry that we have to cut the questions short, but please do send them in, either email them to myself or to Jerry, and the same for the Zoom people. Just take that bit of insurance and email your questions in, and we'll make sure you get them answered. Just very briefly to say, the Haggas have got a meeting on the 30th of April about imaging every planet in the solar system. That's by Ivana Peranik. Our next meeting here is May the 8th, when we've got Chris Crow giving a talk on the Star Trek astrophysics. And of course, our AGM is on May the 15th on Zoom. Just before we disappear, is there anyone who could give Simeon a lift back to Hatfield Railway Station? Not necessarily. Okay, right. Thank you very much indeed.
Can I just,
And again, sorry, Jerry?
can I just mention a couple of quick things?
quickly.
First of all, did any of you see the eclipse on TV? Yeah, the NASA coverage was excellent. BBC's coverage not so, because in their report, which was recorded actually in America, but they didn't check it, the journalist said that it was an amazing astrological phenomenon. More seriously, we've recently lost Peter Higgs, who was the British science physicist who predicted what became known as the Higgs boson, which effectively defines mass. I actually met him a few years ago, just after the discovery was made. And I said that I've been saying for years that if the Higgs boson is actually detected, it should be celebrated with a martini, actually a Large Hadron Collider. Follow that.
I can't follow
Yeah,
that.
no.
All I want to say is thank you very much indeed to everyone for coming along, making it a great evening, particularly to our two speakers. Thank you very much indeed, Jerry, Simeon, and I wish everybody here a safe journey home. Thank you very much for coming. Good night.